Okay, welcome to the next in our series of ferroelectrics, and really glad to have Max Stengel today. I'll introduce him in a second. I just want to remind everyone I'm from the Carnegie Institution for Science, and we've been having these once a month on the second Thursday of each month, 10 a.m. Eastern time, and so please keep joining us. We're really glad to have you. And I'm going to, okay. I want to thank the organizing committee who helps put this series together. Laurent Belay, Cyrus Dreyer, Anna Grunebaum, and Beth Noadnik. And today, Laurent Belay will be joining as a panelist. And so we're glad to have him here with us again today. So we're really excited to hear from Max Stengel from Spain, from Barcelona, and he's going to talk about a really exciting topic, translational covariance of flexoelectricity at ferroelectric domain walls. And Max has a background, well, very working on very interesting things. He's currently has a ERC Consolidator grant working on flexoelectricity, which is his main research focus, and I'll let him explain what that is. He was in Santa Barbara with Nicola Spalding and joined ICMAB in Barcelona in 2011. So he's done a lot of really interesting stuff. I would say almost everything that he's done, well, maybe everything that he's done, has broken new boundaries, and both in terms of techniques and an understanding of materials and real materials, like ones with surfaces and electrodes and domain walls and so forth. And I don't want to take up his time, so we're going to go immediately to him so that he can have his full time to talk, and really excited to hear what he has to say. So Max, you can go ahead and share your screen. Oh, what happened to my mouse?
Okay, let me go ahead. Here it is, full screen. Okay.
Great.
Great. So thanks, Ron, for the introduction. And I would like to thank the organizers for inviting me to give this seminar. So I always like a lot the Ferroelectrics workshop in January. And I think this is a great initiative to keep us going and keep in touch in these sort of challenging times. So thanks a lot, and I'm very happy to be here. So my talk will be about domain walls and flexoelectricity. But let me start from the very beginning with ferroelectrics, which are materials that you all know very well about. Ferroelectrics are materials that typically have a phase transition from a high temperature, high symmetry phase. For example, this can be a cubic perovskite, like in the case of barium titanate and other well-known ferroelectrics, to a low temperature phase, which is polar. And the phase transition can occur into one of the symmetry equivalent states with a polarization pointing either up or down or left or right. And the main characteristic of these materials is that they're switchable with an electric field. So in a macroscopic sample, the phase transition occurs usually not in a homogeneous manner, but the sample breaks into domains with polarization pointing in different directions. And actually, the boundaries between different domains, which are called domain walls, are quite interesting and are actually considered an emerging class of 2D materials with new properties that can differ quite a bit from the bulk properties. So at a domain boundary, we have the order parameter, which is the polarization in this case, switching sign from a down polarization on one side to an up polarization on the other side. And this means that two things, actually, right at the domain wall, the main order parameter vanishes, which means that secondary degrees of freedom can emerge and contribute to the functional properties of this structure. And also it means that the local crystal symmetry is not the same as in the bulk, because there is a spatial variation in some structural distortion or some other order parameter. And this brings about gradient couplings with a whole bunch of new functional properties. And this is what we'll be mostly interested in this talk. So some examples of things that can happen at the domain walls, this is all well known. For example, it is quite curious that until a short time ago, the domain walls in typical ferroelectrics like barium titanate were assumed to be quite simple with an Ising-like structure, which means that the orientation of the polarization is just along one direction, and the polarization goes to zero right at the domain wall, and it doesn't acquire different components. But actually, this has been discovered to be too simplistic for realistic structures, which in many cases acquire some secondary components that can be oriented either along the normal to the wall or in a different plane. And one example is the bichiral walls that were predicted by these two theoretical works. Even more exotic things can happen, like the domain walls themselves can become a new ferroelectric material embedded within the main ferroelectric material, in that a secondary order parameter can be is still unstable and can switch from one side to the other parallel to the wall. And this was shown also theoretically in this work by Jacek Vojdel and Jorge Iñiguez. Of course, this is just the basics, and nowadays things got quite a bit more sophisticated. There are reports of interesting topological structures, like in strontium titanate, lead titanate superlattices. This is very famous work by Ramesh. This is an experimental image of a vortex structure occurring in the lead titanate layers. And also these secondary components at the wall can give rise to topological structures like skyrmions, as was also shown still by Jorge Iñiguez in this work. So there are a lot of things, a lot of interesting things happening at domain walls, and we want to understand them from the point of view of the theory. And the question is what theory to choose to achieve the best theoretical descriptions. And of course, the most obvious choice is the most traditional choice is a continuum model, phenomenological, based on Landau, Ginzburg, Devonshire equations, which is a very efficient approach because it's based on very few parameters and degrees of freedom, and provides a rather intuitive and transparent picture of the physics that is determining the different functional properties that we're interested in. On the other end of the spectrum, we have the first principles approaches that have become very popular nowadays. And the main advantage is that these are free from arbitrary assumptions, free from input from the experiments. They are unbiased, and so they are really considered as predictive in terms of getting from fundamental theory to some real material properties. The main drawback is that these are expensive methods. We can consider only a small number of unit cells, a small number of atoms. And another drawback is that they provide often too much information, in the sense that the amount of data that is processed in first principles calculations is enormous and involves electronic degrees of freedom, structural degrees of freedom. And so mapping this into a simple intuitive physical concept can be often quite tricky. So a good compromise between the two is the effective Hamiltonian approach that on which Laurent Belèche has worked a lot in the past 2 decades or so. And this constitutes a sort of coarse graining of the first principles Hamiltonian, getting the most relevant degrees of freedom and extracting their interaction and building a model that is still has the first principles accuracy, but on the other hand, it can be used to tackle more complex structures. And this is a good compromise between the two. However, in this talk, we want to try an alternative route, which is sort of considering the continuum LGD approaches like a possible new type of second principles methods. So something that we can build as a well-defined approximation to the first principles Hamiltonian, and that can be systematically constructed via some controllable operations and can be also especially validated with respect to a well-defined microscopic model. And this is the link we're trying to establish right from first principles directly to continuum, and this is the main topic of this paper that also Ron has shown at the beginning, that has been published a couple of, maybe 2 weeks ago, 1 or 2 weeks ago. So this is really timely to give this Ferro lecture right after this paper has been published. And this is in collaboration with Osvaldo Dieguez. You see a picture here, and he's working at Tel Aviv University. So let me get started with the model system we'll be dealing with. So this is not really, my main focus is not really in getting new properties, new sophisticated or complex structures, but sort of working on simple ideas on a very simple model system, and try to see how we can do this link between first principles approaches and continuum in a case that is free from additional complications. So the material we'll be dealing with are our beloved AbO3 perovskites. The structure is sketched here. We have an A-side cation that can be barium or lead. And then we have an oxygen octahedron with the B-side cation in the middle. That can be typically titanium or other type of transition metal atoms. We'll be focusing on an Ising type 100 oriented wall, which is one of the main pseudo-cubic axes, with a one-dimensional polarization that is always oriented along the 0, 1, 0 direction, which we'll call Y in the rest of the talk. So the continuum description of this model is a very simple equation. It has only 3 terms in the most basic picture, and these 3 terms has a very intuitive explanation. We have the homogeneous double well potential of the both ferroelectric, and we add a gradient term that penalizes inhomogeneous structures, because the polarization wants to be homogeneous, and these walls emerge because of entropy, but have a certain energy associated to them, an energy cost, which is sort of conveyed by this G coefficient in the continuum Hamiltonian. So we solve this as an analytical solution, which is an hyperbolic tangent of the coordinate normal to the wall. This P0 is the equilibrium solution of the both potential. And then we have a scale parameter, which is also called correlation length, which determines the thickness of the wall, is this psi, and is the competition between this gradient term and the sort of the curvature of the Landau potential near p equals 0. From this, we can calculate many interesting properties of the wall, like the energy, for example, which is given roughly by the thickness of the wall times the bulk energy of the, which is the minimum of the Landau potential. So this is all well known and quite simple, but what we want to do with this is get these parameters from first principles via a sort of well-defined and controllable procedure. And to do this, the first thing we need to worry about is how to map the continuum fields to the microscopics. So we start with some arbitrary function, which is our order parameter as a function of x. And we want to get out of this, we want to have some device that from this py, or from an arbitrary inhomogeneous py of x, we get a well-defined distortion, a well-defined lattice distortion, which we describe as a UL of k alpha, where k is a basis index, a is a direction of the displacement of the atom, and L is a cell index. So we want to do this back and forth. So we have to, our goal is to establish a two-way mapping, because the direct mapping is needed to determine the model coefficients, and the converse mapping back from the atomistics to the continuum is needed in a way to validate the model against the reference first principles engine. The goal we have, we set to ourselves is that we want an exact theory in the limit of small distortion amplitudes and smooth structures. So small distortion amplitudes is already part of the usual assumptions of Landau theory, because you have this polynomial expansion in the order parameter amplitude. But here we add one more requirement, which is smooth structures on the scale of the cell. And this is natural to require from a macroscopic theory that is built from the atomistics. So let us focus first on the direct mapping that will serve us to get the coefficients, and then come back to the converse mapping that will serve as a validation of what we get. In the homogeneous case, things are pretty simple and actually quite well established, in the sense that people have been doing this many different ways in the past 20 or 30 years. And to get the sort of potential energy landscape of the homogeneous polarization, what you usually do is relax in a first principles calculation, the tetragonal structure, the polar structure, and the cubic structure, and then calculate the distortion, which is the difference between the atomic positions in the two cases, and from those extract some polar displacement pattern, which is can be actually exactly equivalent to the distortion, but we allow for some P0, which is a sort of scale parameter that decides a little bit the units in which we express our polarization. Typically, the polarization is a polarization, so in Coulomb per meter square. But in this case, in ferroelectrics, what we have is that the polarization is dominated by a lattice distortion. So in the context of this work, we found it more natural to express P0 in length units, so as you would expect for a lattice displacement. And this Py of k is actually becomes actually a dimensionless set of 5 numbers, where k runs over the 5 atoms in the unit cell of the perovskite. So once we have this this distortion pattern, we can just generate a set of atomic configurations whereby linearly increasing the amplitude of this distortion starting from the cubic structure, and this allows us to draw from first principles the double well potential, and therefore access the parameters A and B. This is very straightforward. So the trouble starts, and the real, actually, the real challenge of this work and the main conceptual value starts when we consider spatially inhomogeneous fields, because we have to think on how to map some polar order parameter that is not uniform in space onto some lattice distortion. And what we do is to choose the following formula, which is associating the distortion pattern ULK alpha as the zone center distortion of the cell multiplied by the amplitude of the field, of the polarization field, right at the unperturbed atomic site. So this is a cell index. This is some function that runs over the whole crystal, and this is no longer cell periodic. So what we have is that if the polarization field is a constant, of course we recover the previous slide. So we have a uniform displacement of the titanium, of the barium, of the oxygens, and here is a sort of legend that tells you what these numbers correspond to. In the case of inhomogeneous distortion, here we have a trigonometric function. What we have is simply that it's quite intuitive. So we have the zone-centered distortion like here, but we modulate it in space by the field, which acquires the meaning of a sort of envelope function. So this allows immediately to get the macroscopic limit and therefore to predict from first principles the parameter in the Landau in the Landau expansion. In the Landau expansion, we had this A and G. A was the harmonic coefficient, and G was the gradient coefficient. If I consider monochromatic polarization waves, like the sinusoid in the previous slide, I get the second derivative of the energy with respect to this parameter as A plus GQ squared. So G is nothing but the spatial dispersion of the harmonic coefficient of the associated with the polar mode. And by doing what we usually do in first principles theory, so calculating the interatomic force constants, it turns out that what we have to do with this very basic ingredient is just to calculate the second moment in real space by multiplying the force constants times the difference of the positions of the two atoms and doing a lattice sum. And then what we have, this phi2, we project the result onto the polar mode, onto the polar distortion that I defined in the previous slide. And this defines the gradient coefficient G. So this seems all good, and it seems like we have solved the problem, but actually there is an issue, and this issue is key to understand actually what we have done in this paper, because this distortion actually is not well defined. We had before some ambiguity in the unit, but that was trivial. Now we have a sort of more serious ambiguity in that when we relax the ferroelectric structure, we can do it in many different ways. For example, we fix the barium atoms and we let the other atoms relax, and we get this kind of pattern. But we can also fix the oxygens, and then we get a different displacement pattern. And the thing is that as long as we stick to homogeneous distortions, these two are perfectly degenerate because they're related by a rigid translation of the polar phase of the crystal. And so the double well potential that I get from this or from this is exactly the same. So trouble starts when I get to when I use the prescription I defined in the previous slide to define modulated structures, because this sort of translational arbitrariness in the polar mode leads to different results for the modulated structures. And so this is clearly a fundamental difficulty, because I want to extract the gradient coefficient G from the energetics of this kind of patterns. And if these patterns are not well defined, these have clearly different energies, then I'm stuck. So we can do two things at this point: either stop and move on to another problem, or just start wondering of what is going on. So, and the idea we had is that actually the problem comes from the fact that we are missing something in the continuum model that I showed you a few slides before. So that it might be too simplified in order to get a correct physical answer. And the idea we had is to try to throw flexoelectricity into the mix. So this sounds like a random idea that comes from nowhere, but actually there are some good motivations for it. But let me try to explain what is flexoelectricity first. So we have various manifestations of flexoelectricity, and the most common, the most well-known one is a direct effect, where a polarization is generated from a uniform strain gradient, like in this cartoon here. I bend the sample and I get a uniform polarization out of it that is oriented normal to along the radius of curvature. Actually, we can have also a converse effect where a uniform strain emerges from a gradient of the polarization, like in this case, and this is a sort of illustration of this idea. And actually, the two effects are governed by the same flexocoupling coefficient F, and one can show that these two, if you do a simple integration by parts, are exactly equivalent at the bulk level. You can decide to include either one or the other in your continuum Hamiltonian, and as long as you don't have surfaces, the description is exactly the same. But actually, we prefer to work with this one because it is most relevant to ferroelectric domain walls. And the reason is simple, because here the main order parameter is the polarization, and the strain only emerges as a slave, as a secondary effect of the gradients of the polarization, which is essentially what this coupling is doing. So how do we include the polarization? Well, we have this revised continuum model, which is exactly the same as before. I just added this converse flexoelectricity and the elastic term, which is, of course, the harmonic potential for the strain. And we solve it, and it is convenient, actually, instead of the strain, to use the displacement field U, and the strain is simply the gradient of this displacement field. And what we find is that we can, for a given configuration of the polarization, we can exactly integrate out the displacement field, which is given by this formula, and actually remove the strain as an explicit variable from our Hamiltonian via a renormalized gradient coefficient G tilde. And this shows that we have the same solution as before, like an hyperbolic tangent for the polarization, but plus, in addition to that, we have an elastic offset. So a macroscopic displacement, elastic displacements of the two domains, that is this delta U, which is given in terms of the bulk polarization, the flexoelectric coefficient, and the inverse of the elastic constant. And actually, this effect was discussed in this review by Peter Yudin and Sasha Tagantsev, and then in other papers. So let's go back to our long wave method and see if the inclusion of flexoelectricity actually addresses our problem. So we have a new mapping from the fields to the microscopics, which is exactly the same as before, but we added this term, which is the elastic field. And this is quite trivial because the mapping from continuum to the discrete distortions is just some local displacement of the atom, which is proportional to the displacement field, as you would expect for an elastic wave. So we go back to our long wave approximation and try to recalculate the gradient coefficients, which are G as before, which is the gradient coefficient for dP and dP. But now we have two new terms. One is the flexocoupling coefficient, which is given by this formula, a very similar formula, actually. We don't have 2P, but we have only 1P. And the coupling to the elastic degree of freedom is simply a sublattice sum. And then we have also the elastic constant, which is the same coupling where we have the displacement field and the displacement field. And it might sound quite odd to find the elastic constant in a context where we are discussing gradient couplings, because our understanding of elasticity is as a uniform degree of freedom that does not change the lattice periodicity. But well, in a sense, it does change the lattice periodicity, but it doesn't make it doesn't break translational invariance. But actually, it is true that the elastic constant falls in the same category of these two these other two couplings as it is a gradient effect at second order in Q only in the displacement field. So we can check that what we have been doing so far is correct by looking back at the literature. And this definition of C that emerges from what we decided to use as a mapping from the continuum to the discrete model correspond exactly to Born-Huang's classic formula in terms of a lattice sum of the force constants. Also, this result for the flexocoupling coefficient matches the established first principles theory as we know it after the work of my own work and David Vanderbilt's work, etc., etc. So let's go back to the problem we had at the beginning about the translational freedom that kind of spoils our party. And we do again this exercise, so modifying the ferroelectric distortion pattern by assuming some rigid translation. This lambda is sort of a measure of this translational freedom in the uniform ferroelectric distortion. So if we go back, I don't have time to go through the algebra, but believe me that the new flexocoupling coefficient transforms as F plus lambda C. Well, C is the elastic constant. So even flexoelectricity is not well defined. And G, we knew already that is not well defined, and it transforms like this. So both quantities are not well defined in the theory, which is something that might be shocking to some Landau theorists that has been assuming that these are well-defined physical properties since the very beginning. But actually, what we find is that the renormalized coefficient, which is a combination of F prime and G prime, is the same as it was before. So this is actually an invariant with respect to this transformation. And this means that I get the same solution for the polarization, the same energy and wall thickness, which are what I consider the main physical properties of our system. I only get a different solution for the strain, for the elastic displacement field, which does depend on this lambda. So this sounds like black magic. So I just added a random physical property like flexoelectricity, and I got some exact invariance of some properties of my Hamiltonian. But actually, this is just a manifestation of a more general covariance principle, which can be understood by recalling again the mapping between continuum and discrete distortions. And if we consider this transformation, which is changing simultaneously the polar distortion pattern and the elastic displacement field by the same parameter lambda, what I get, you can plug this into this formula and get that the microscopic distortions are exactly the same. So these two sets of fields are actually the same macroscopic representation of the same, actually two different macroscopic representation of the same microscopic structure. So it is quite natural to impose, to require that any continuum functional must be covariant with respect to this transformation. So this must not affect what I regard as my physical properties that I extract from the model. And this, on the right side, you have a sort of pictorial representation of how this works in the context of a ferroelectric domain wall. You have the atomic structure here. you can change the definition of delta U and of the polar distortion, and you get two different pictures from the same atomic structure. And this is what I just said before. We must treat together F and G, flexoelectricity and polarization gradient, in order to get a well-defined theory. So this has a worrying consequence, which is that the strain is itself ill-defined. In what situations is it ill-defined? This is easy to see from what I showed you before. Let's work with the symmetric strain for a moment, which is defined as in this formula as a gradient of the displacement field. And let's do the same transformation as I indicated in the previous slide, which is subtracting lambda times the polarization. What we get is that the local strain becomes ambiguous only in presence of an inhomogeneous polarization field. So this sort of machinery is closely bound to how flexoelectricity works, because it is related to situations where your polar degree of freedom is non-uniform. And this is maybe why only now we get to understand this point that seems quite simple and basic, just because we didn't worry about flexoelectricity before. So it might take a while actually to rationalize the fact that strain is ill-defined whenever a polarization is non-uniform. So I just add a slide to convince you that this is actually the case. And so this is actually something that we might want to do as well, which is having an atomic structure, which I plot here as a set of lattice distortions, and have as a goal to extract from this structure a macroscopic information, which in this case is the strain. So we start from here. The first thing we do is sort of interpolate the atomic positions with some lines, the sort of macroscopic approximation to this set of lattice distortions at the level of the single sublattices. And then what we find out is that to get this into a strain, we need to do a weighted average over the sublattices. And these weights are what sort of, in a way, contain the arbitrariness of the definition of the strain, because there's actually no physics principle that tells me what weights should I choose, whether I should give more priority to the heaviest atom, as it's done usually by microscopists, just because these are brightest in images, or whether I should scale them by atomic masses. Okay, this is fine for dynamical problems, but why should I worry about masses in a static structure like a ferroelectric domain wall? Also, equal weights, like the more democratic principle, sounds reasonable, but it is just one choice among many possibilities. And none is right or wrong. And this is something that we can call a weight freedom. And these weights are only defined by a normalization condition, that they must sum up to 1. So we have the correct strain from the weighted average. And what happens is that the weights, in a way, determine what is the center of mass of my polar mode, because there is this orthogonality condition between the polar and the acoustic mode that must be satisfied. And in a hand-waving manner, we can state this as saying that the polar mode should not displace the cell. So the translational covariance that I discussed before can be equivalently expressed as a weight freedom. And actually, this is brings us even closer to the first principles theory of flexoelectricity, because we knew already actually that the flexoelectric coefficient is not well defined and depends on these masses in a way. So if you bend a sample and you extract the forces, the atomic forces from some cell located in the middle of your pattern, you get something like this. And these forces actually are enjoy a sum rule. So these are related to the elastic coefficient, and this tells you physically that a macroscopic strain gradient puts an elastic force on every unit cell of your crystal. And this is problematic when I want to extract from these forces some atomic distortion, as we want to do when calculating the flexoelectric coefficients. We need to remove this net elastic force to be able to calculate a polar distortion in flexoelectricity. And this is done precisely by using some weights that are arbitrary. And this matches what I said in the previous slide about the definition of the strain. It is the same issue, just two different manifestations. So this is enough, I guess, for the conceptual part. Let me get into the numerical test. We decided to validate this model by choosing three well-known materials, which is barium titanate, lead titanate, and potassium niobate. We also tested on a few more materials, but these are a different ground state in their equilibrium structure, so they're less informative from the point of view of the physics. So, as I said before, we consider 180 degrees domain walls all along the 100 direction. And just for testing, we consider both domain walls that are centered on an AO plane, which is here, or a BO2 plane. So, of course, a continuum model cannot capture the difference between these two configurations, just because we remove from the lattice model any information about the atomic, the registry with the atomic structure. But it is still interesting to look at both to see whether they're close, whether they sort of match with what we get from the model. So, to test our covariance principle, we'll use two choices of the weights, either equal or scaled by masses, and see whether it is true, as I try to convince you that the physical answers are the same. And just to add one more challenge, we used an in-house PAW code written by myself, which is very user-unfriendly, so to test these ideas in the worst possible conditions. And actually, I didn't mention before, but I always worked at fixed cell parameters. We don't relax the structure, the macroscopic strain, just to keep things simple, because this the macroscopic strain would add more degrees of freedom in the system, and we want to test these ideas on the simplest model possible. So this is what we get for the domain wall structures. The symbols are the relaxed DFT distortions. The curves are the continuum solutions. And actually, I find it quite remarkable that we can get atomic positions from the continuum model. But this is, and it is quite ironic, actually, that the continuum model gives gives a unique answer for the atomic positions, but an ill-defined answer for the strain. This is sort of ironic if we consider that the strain is usually considered as a typical macroscopic degree of freedom. Anyway, in the case of, for all the cases we considered, we have a remarkable agreement between the predictions of the continuum model and the structure that comes out from the DFT calculations. And this is especially remarkable if you consider that the ferroelectric domain walls in these materials are very thin, are just 1 unit cell thick, which is usually considered as something not well described, a regime where the continuum model should break down. And yes, we do find that the continuum results are independent of weight choices as expected. We can test the translational covariance actually by looking at the local center of mass of the cell, which is weighted in 2 different ways. And actually, you can see that the displacement field predicted by the model reproduces quite accurately what we get from the atomic positions if we weigh them in a consistent way with what we do in the construction of the model parameters. Interesting, we have the same elastic offset at AO and BO2 centered walls, which means that this property is not really sensitive to the local atomic structure of the wall, but is a truly macroscopic thing. And we have a slight overestimation of delta U, but this is something we could expect in a system that is quite so far away from a regime where the continuum approximation is considered to be justified. So these are the results we got for energy and thickness. You can see in all cases that the agreement is not perfect, but is quite good. Actually, it is very close to either one, either the AO or the BO2 result from the first principles calculations. And this is quite also, again, quite remarkable given the simplicity of the model that we're using. And again, the thickness is, the sigma parameter is half a unit cell in all cases, which means a thickness of about 1 unit cell. And here we have two lines for barium titanate. And this second line looks quite different from the rest of the materials in that the domain walls are much thicker. And this is a barium titanate crystal under an isotropic 1% compression of the lattice parameter. So why did we consider that? We want to test the model in a context where the macroscopic approximation is justified, because I told you about, at the beginning about this exact limit that we want to enforce in our theory. And this is precisely the regime that we want to test. So to get thicker walls, so we need to reduce the A parameter, the sort of the instability, the strength of the instability, which is usually done either by controlling temperature or pressure. We used pressure and strain just because it is much easier to do in a first principle calculation. And this is what we get for the energy and equilibrium structure. So in all cases, we get an agreement that is essentially of the order of the numerical accuracy of our calculations, which is a stringent test of the correctness of our model. So I don't know how much time I have, but I wanted just to discuss briefly the parameters, just because this is what a Landau theorist might be interested in. And again, we have different parameters depending on the weight convention. In the case of equal weights, this is what we get. And it's particularly interesting to compare the two versions of barium titanate, because typically in Landau theory, we have critical parameters that are supposed to depend a lot on external perturbations like temperature or pressure. And this is the A parameter. And the other parameters are supposed to depend much less on external conditions. And this is exactly what we get here, as you see from our study. Then we can compare the equal weights with mass scale weights, and you get very different answers for the flexoelectric coupling and the gradient coupling, but actually the renormalized gradient coefficient is exactly the same as I expected. So it is curious to compare this with phenomenological theory, and fortunately we get exactly the same answer for the renormalized gradient coefficient as it is usually taken in macroscopic theory. So this is a very simple model. We are doing a lot of ongoing work about to make it more complete and more physically interesting for realistic structures. Of course, we need to generalize it to 3 dimensions. We need to consider electrostatics, longitudinal fields. We need to add other contributions to the strain, most notably electrorestriction. And also, it would be nice to consider other degrees of freedom, like the AFD tilts. All this is under control. I would spend probably 2 more hours to discuss it, but now I'm over with time. And please ask, I have a few slides in case you're interested. So I'll just place the conclusions and thank you for your attention.
Okay, great. Thank you very much, Max. That's great. Please, everyone, I should have mentioned at the beginning, please type questions into the Q&A panel on your Zoom app, and it's even possible to ask something out loud if you feel like that's necessary. So we're going to start with Laurent. So Laurent, you're on.
Okay, thank you, Max. Super nice. One question is, for example, if you look at PTO-STO superlattices, you have up and down domains, and in the domain walls, you have vortex that you show in the picture. So to describe vortex, it's not polarization, it's like electric toroidal moment as the order parameter, which is like R cross P. In your method, can you get this vortex configuration, or just by having, I don't know, the terms that you have and perhaps depositing field, or do you need to add a new order parameter, which will be the electric toroidal moment?
This is a very good question. I think that my feeling is that you can do everything with the polarization. Just I mean, you can whatever you can get as a long wave approximation of an atomistic structure, whatever makes sense to study in a long wavelength context with macroscopic ideas. I think you can tackle with this kind of approach. In the case of vortices, it's a very good question to know what you need in order to get that out of the polarization. And well, I think that of course you need a few more coefficients than what I showed, just because there's not only one component of the polarization. You have also the other component of the polarization. You probably have strain fields, so you will need to consider electrorestriction as well. But I think it's quite feasible if you sort of decide the boundary conditions. Then, the question is whether how far you push your approximation, how many orders, how many powers of the order parameter you take, how many powers of the gradient coefficients you take. But in principle, if you have a smooth structure, you should be able to capture it within this approach.
Thank you.
Okay, great. We have some questions typed in. Ina Ponomarev asks, is the model extendable to finite temperatures?
Is the model extendable to finite temperature? Okay, so there are two extensions of finite temperature we can discuss. Of course, one is making the model dynamic, which means add a mass to your degrees of freedom and simply allow the fields to evolve in time. This would get me, actually, I'm sorry I didn't prepare a slide on the dynamic flexoelectric effect, which is also nicely fits in with this, with the translational covariance I discussed, because it is affected by the same indeterminacy with respect to what you choose as your polar distortion. And if you put it in, then you get an invariant dynamics of your degrees of freedom. So you can definitely do temperature with some kind of Monte Carlo solver. The question is whether this is enough to get a realistic temperature in your system, or whether you need to consider other degrees of freedom that you haven't, that are not the macroscopic polarization or the strain. So this is a question that you might need to modify also the way you extract your coefficients from principles, because you might want to get a temperature-dependent coefficients from your first principles macroscopic model. But anyway, I think this is doable in principle. Might be heavy to compute, but doable in principle.
And Bo Wang has a question. He says, very interesting work, great talk. I have one question. In the continuum model, you didn't include the direct flexocoupling term, but only the converse term. Does it change the translational invariance if both terms are considered?
Oh, well, well, it doesn't change anything. So essentially, when this is the energy functional, and once you what you need is not necessarily the energy functional, but the constitutive equations for the stationary solution of the energy functional. And this is once you derive your functional with respect to the polarization and with respect to the strain, you get exactly the same equations if you consider either the direct or the converse form of the flexocoupling coefficient, of the flexocoupling. So they're related by a translation, by integration by parts. So if you write them in reciprocal space, it's exactly the same quantity.
I have a question about at the beginning with when you show the dependence on defining the displacements on which atom you keep fixed. But then later on, you talked about keeping the center of mass fixed. I mean, if you kept the center of mass fixed at the beginning, it seems like there would be no ambiguity. Is that fix everything, or you still have a problem?
Yeah, this is the thing. You know, you in order to fix the center of mass, you need to define the center of mass, and to define the center of mass, you need to put some weights on the different sublattices. And these weights can be just the average of all, so you can define the center, the average position of all atoms by choosing these weights equal for every atom, or you can just look at the physical center of mass, or you can just say, okay, all the mass is contained in barium and all the rest is irrelevant. And you get three different definitions for the strain for your center of mass, but in the end, if you follow all the prescriptions I discussed for constructing the model coefficients, then you get exactly the same answer. So the thing is, there is no good there is no preferred way there is no right or wrong way to choose your center of mass or the definition of the center of mass. They just give you different definitions of the strain that are all equally good. The thing is,
if I can just follow up, I mean, it seems like if you use the masses, that would be necessary for, to have constant momentum of your system. I mean, of your total system. But I understand the problem is you end up with something that depends on the masses in spite of it being a static property. But
exactly, yeah. So this is a static problem. So it shouldn't depend on masses. And so if you put the masses in the definition of your coefficients, then your results will depend on the masses, and this is not good. But what I showed ensures that actually the final result does not depend on masses, even if you use masses for the construction of your model.
Right. Okay. Good. But Wang has another question. He asked if the mechanical boundary conditions influence the invariant relation.
Well, I would say no. I guess we tested this by considering barium titanate under hydrostatic pressure. So this gives you a sort of different boundary conditions, and we have a perfect the invariance relation is perfectly respected, and in that case, I don't think there's anything that you need to be especially careful about in the context of the mechanical boundary condition.
Well, let me just follow up on that myself. So, and then then we're going to have to wrap up because we're out of time. But if you consider, I mean, this goes back to classic work on elasticity and so forth. I mean, if you for polycrystals in ceramics, if you consider like constant strain conditions or constant stress conditions, you get two different mechanical behaviors. And then reality is somewhere in between. But it seems like in your case, it seems like it should affect the value of, for example, the flexoelectric coefficients. So if you evaluate those at constant stress field or constant strain field, it seems like they might be different or not.
Well, okay. So this is a very interesting. Question. Actually, now that you explain it to me, now I see that it's really interesting. Just because so there are clearly some ambiguities, and there were some paradoxes pointed out in the literature when you plug in some gradient terms in your Hamiltonian. There might be some ambiguities of between the constant stress or constant strain conditions, and I think that what we did it precisely solves that kind of paradoxes. And I had this was I had one slide that I don't know if I'm allowed to say anything about it, but let me try. So yeah, so essentially is, well, maybe this one about, well, this takes too long to explain, but anyway, so you by itself, so flexoelectricity in a way is a non-analytic elastic contribution to the gradient coefficient. You know about non-analytic electrostatic contributions, but here when we look at dispersion effects, we get also non-analytic elastic effects, which makes sense because the elasticity is also long range, like electrostatics. And so your renormalized gradient coefficient is a non-analytic object, but once you but you can actually show that when you write G and F, the individual flexoelectric and gradient contributions, the way I described, you take care of that exactly. So there are no ambiguities anymore, and the only ambiguity is in the separation between something that is analytic and non-analytic, and this is and this has some degree of freedom, but the result is always well defined. And so this is I think this is this might be quite powerful to solve some long-standing debates about what to do in cases where one uses strain or stress, etc., etc.
Okay, fantastic. We're going to have to wrap up. I want to just say a few concluding things. Let's thank Max Stengel again for a fantastic talk. And I'm going to go ahead and steal the screen here and okay. Just say a few closing remarks. So we've had a series of these talks going back to over a year ago, well, to April 2021, and you can see videos of these talks online. So you can either go to the website that's mentioned in the email, or you can just Google Ferroelectrics and you'll find the videos. And next month we will meet on August 11th, and Claudio Cazorla will also in Spain. We'll talk about novel piezoelectric materials for photocatalytic water splitting. So we're looking forward to that. And don't go yet. I want to mention again, keep your calendar free for the workshop February 5th to 8th in person, Golden, Colorado at the Colorado School of Mines. And Megan Holtz is the local organizer for the meeting. And we will be sending out announcements sometime in the next month or so, and the first announcement, and after we have enough to say about details, and the deadline for abstracts and so forth will probably be December 1st, like in previous years. So please keep that in mind, and thank everyone, and we'll see you next month. So thank you, and I'll say goodbye.
Thank you, Ron.